Hi and welcome back. In this video we ask what happens to the output of a system, of a dynamical system, with a transfer function g, if we apply to the input a sinusoidal signal. So what happens if u of t is a times sine of omega times t? Of course you know the answer, you know how to answer that. Take the signal, which is in the time domain, and apply the Laplace transform. So the S-domain signal becomes u of s is a times omega over s squared plus omega squared. And given that we have the transfer function of the system, we know that the output now, again in the S-domain, is the input times the transfer function. So the output is g of s times u of s. Namely, it is g of s times a omega s squared over s squared plus omega squared. And now we can apply the inverse Laplace transform to obtain the output of the system. That's alright, and now we know how to determine that inverse Laplace transform. We have to perform a partial fractions expansion and so on and so forth. But there is a problem here. First of all, it is quite cumbersome to determine that partial fractions expansion. One reason is because of that term here. We have a pair of imaginary poles, and second, we have a transfer function which might be quite complicated. So it is quite some effort to determine the inverse Laplace transform, and if possible, we would like to avoid it. And let's say we take the pains and we determine the inverse Laplace transform. Even if we do that, the result can be quite complicated, so it can evade further analysis, or at least that will not be easy to do. Instead of doing that, we will give a very simple theorem that allows us to determine the frequency response of the system after a long period of time. That frequency response is called the steady state frequency response. Let's state the theorem. The theorem states the following. If we know the transfer function of a linear dynamical system, and we know that it is stable in the bounded input, bounded output sense, and the system is excited with a sinusoidal input of the form a times sine of omega t. This is nothing but a sinusoidal signal of amplitude a. Then, after a long period of time, at t much larger than 1, the system output can be approximated by the following expression. The amplitude, here we have a sinusoidal output as well, but the amplitude of that output is not a anymore. It is a multiplied by a factor r infinity. So here we have a sinusoidal response of a different amplitude, which is a times r infinity. It is sinusoidal, it has the same frequency, the frequency doesn't change, and the system response can be shifted on the time domain by an angle phi 0. This is called the lag, the phase lag. Phi 0 is called the phase lag, and r infinity is called the amplitude ratio. Now the good news is that this theorem allows us to determine the amplitude ratio and the phase lag, and in fact they are given by very simple formulas. The amplitude ratio r infinity is given by the modulus of g at j omega, and the phase lag phi 0 is the argument of the exact same complex number. It is the argument of g evaluated at j omega. And since we're talking about the modulus and the argument of a complex number, let us recall certain properties of the modulus and the argument of complex numbers. For the modulus, we know that the modulus of a quotient is the quotient of the moduli. So the modulus of z over w is the modulus of z over the modulus of w. Of course, for that to make any sense, w must not be 0. And secondly, the modulus of z times w is the modulus of z times the modulus of w. These are very important properties that we must keep in mind. Now, second, about the argument, we know the following properties. The argument of z over w, the argument of a quotient, is the difference of arguments. And the argument of a product is the sum of the arguments of the two complex numbers z and w. Here again, for z over w to make sense, w must be non-zero. Thirdly, one more important thing, just let me remind you, although I suspect you already know, some properties of the exponential of an imaginary number. If you have the imaginary number e to the j times theta, where theta is a real number, then this has a modulus equal to 1. And the argument of e to the j times theta is exactly equal to theta. Now, with these properties in mind, that's all the math we need to know. We can solve a few exercises, we can solve a few examples to understand how we can use this theorem in practice. We will try to solve these 5 problems where for every such transfer function, we will suppose that we give this input. We will give the input a times sine of omega t, and we will try to approximate the output of these dynamical systems at very large times, at t much larger than 1. In other words, we will try to find the steady state frequency response of these systems. And let's start with the first one. So example number 1, take this function. And let's apply the theorem. Now the theorem requires that the transfer function must be BIBO-stable, otherwise we cannot apply it. Is this BIBO-stable? Well, let's find out. Let's see what the poles of this transfer function are. The poles, the solutions of tau s plus 1 equals 0 are s equals minus 1 over tau. And given that tau is a positive number, this is a negative real number. Therefore, G is BIBO-stable. Good, so we can apply the theorem. Now the theorem says that if that's the input, the output after a long time, let me sketch this for you. The output of the system, we don't know exactly what it is in the beginning, but certainly after quite some time, it can be approximated by a sinusoidal function. This sinusoidal function, this ultimate response of the system, is given by this formula, a times r infinity, so that's the new amplitude, a, the old amplitude, times the amplitude ratio, multiplied by the sine of omega t plus phi 0. It remains to determine r infinity and phi 0. R infinity is the modulus of g at j omega. Take g and substitute s by j omega. Now that's the modulus of a fraction, the modulus of a quotient. We'll apply this property here, the first one. So modulus of k over modulus of tau omega j plus 1. K is a positive number, positive real number, so that's just k. And here we have tau squared omega squared plus 1. And that's the amplitude ratio of this transfer function. So that's it, nothing more to do here. What about the phase lag, phi 0? Now that is the argument of g at j omega. We don't have to do anything complicated here. It is the argument of a fraction. So it is the argument of k of the numerator minus the argument of the denominator. What is the argument of k? K is a real number, so the argument of k is 0. So this is minus the argument of tau omega j plus 1. Note here that tau omega is the imaginary part, 1 is the real part. So this is minus the 2-argument inverse tangent function of tau omega, 1. Now look here. The second argument is positive. 1 is positive. Therefore, we can simplify that expression and we can write minus arctangent of tau omega over 1, or just minus arctangent of tau omega. And that's it, we solved the first exercise. And we can tell now that after a long time, after we apply a sinusoidal input to the system, we know that the output will be sinusoidal again, given by this expression where r infinity is a function of omega and phi 0 again depends on omega. A couple of things before we proceed. I want to make sure that you are aware of these formulas. First of all, if you have a complex number in this form, a plus bj, a and b are real numbers, then the modulus of that complex number by definition is the square root of a squared plus b squared, and the argument of that complex number, which is defined provided that z is not equal to 0, 0 does not have an argument, this is equal to the 2-argument inverse tangent function b, a. That 2 here is not a coefficient, is not a number, it is part of the name of the function. It's a little strange annotation for a function. Second exercise, again the same objective. We have a transfer function, we apply a sinusoidal input. What is the output? If the input u of t is a times sine of omega t. In this case, we have to check first whether we can apply the theorem we stated before. The theorem requires that the function must be BIBO-stable. But the poles of this transfer function, look here closely, are plus 1, which is a positive real number, so we cannot apply the theorem. What does that mean? This doesn't mean that the output is not defined, that we cannot find the output at all. Apparently, we can find the output of this system. It is the inverse Laplace transform of g times a omega over s squared plus omega squared. But we cannot benefit from the simple results of the previous theorem that we stated, so there is no easy solution here. If you want the output of that system, you have to determine the inverse Laplace transform of the transfer function of the system times the Laplace transform of the input. There is no other way to go. You must make sure that the system is BIBO-stable before you can apply the theorem. So we'll put an X here and we'll do nothing more. Third example, very simple transfer function. G of s is 1 over s. This is known as a simple integrator. Can we apply the theorem? Let's see what are the poles of this transfer function. The poles are s equals 0. Is this BIBO stable? No, it is not. So we cannot apply the theorem here either. So that's it. We can't apply it. If you want the frequency response, you have to take the inverse Laplace transform. Let's have a look at the fourth exercise. Again, first we have to check the poles of the transfer function. What are the poles? We see here we have -1 and -1/3. These are negative real numbers, so the function is BIBO stable, and we can apply the theorem. So if the input is that sinusoidal input, then the output after a long time, we don't know exactly what will happen in the beginning, but after quite some time, this offers an extremely very good approximation of the system response. And this is A R infinity sine of omega t plus phi 0. First things first, let's determine R infinity. This is the modulus of a fraction. So this is the fraction of the moduli, like that. Here we used this property as well as this property. Now, what is the modulus of this number? In other words, what is the modulus of the exponential of j times something? In this case, the exponential of j times minus td omega. Well, this is equal to 1 over square root of omega squared plus 1 square root of 9 is the square of 3, omega squared plus 1. And that is the amplitude ratio. So we have solved half the exercise. Let's now determine phi 0, the phase lag. Let me better erase this part. Now the second half of the exercise is to determine phi 0, which is the argument of the transfer function evaluated at j omega. So let me better write the argument of g at j omega. Note here the numerator is an exponential of an imaginary number, and we know that we have a property that will allow us to find the argument. Here we did nothing but using these properties. The argument of a quotient is the difference of arguments. The argument of a product is the sum of arguments. The argument of j times minus td omega, according to this property down here, is minus td times omega. Then here we have a tan 2 of omega comma 1 and the same as before, the second argument is positive. That is positive. Here again, this is positive. This allows us to simplify the expression, and instead of a tan 2 we can use the simple arctangent function. If you don't want to simplify that expression, you can leave it like that. An answer that involves a tan 2 is a perfectly acceptable answer. So now we have solved this exercise as well. There is just the last one more to go. This transfer function is the transfer function of a second order dynamical system where k, tau and zeta are positive, and we know that second order systems are BIBO stable. You don't have to take my word for it, you shouldn't take my word for it. You can check that the poles of this transfer function, you can find the poles and make sure that the real part of these poles are always negative. Now, given that, you can do that as an exercise, we can move on and tell what is the steady state frequency response of this system. According to the theorem, the steady state frequency response is given by this expression, where R infinity is the modulus of G at J omega. So let's find that, and then we'll also determine phi 0. Modulus of a fraction. Again, same story. Look now, here we have tau squared, j squared, omega squared. J squared, by definition, is equal to -1. Now, in the denominator, we have the modulus of a complex number, which has this real part, that's the real part, and this imaginary part. So the modulus is given by the square root of the real part squared plus the imaginary part squared. And that is R infinity. Now let us find phi 0. So it is the argument of that complex number. This is G at J omega. We did that right before. So this is the argument of K, which is 0, minus the argument of the denominator. So let's write it down. Minus the argument of the denominator. J squared we know already is equal to -1. So this is minus tau squared omega squared. I will write 1 here. And that's exactly the same as before. That's the real part, and this is the imaginary part. So this is minus a tan 2 of first comes the imaginary part, and second comes the real part. Again, focus on the second argument in this two-argument inverse tangent function. The second argument can be either positive or negative. That depends on the value of omega and the value of tau, of course. So we can't know in advance whether this is positive or negative, and we cannot simplify this further. We have to leave it like that, and that's a perfectly acceptable answer. So we have now solved this last example. In any other case, in any other example, you can repeat very similar steps and obtain the steady state frequency response of your dynamical system. So what we did today is that we presented the theorem, so that if you have a transfer function and you excite it with a sinusoidal input, you know that after a long time you will obtain a sinusoidal output x infinity, which has a certain amplitude. If the amplitude of your input is a, the amplitude of your output will eventually be a times r infinity, and it will have a phase lag phi 0. And once again, the amplitude ratio is the modulus of G at J omega, and phi 0 is the argument of the same quantity, the argument of G at J omega. All that, of course, provided that G is BIBO stable. And with that, thank you very much for watching, and goodbye.